Hello, nice to meet you. In this video I would like to address the first law of thermodynamics. And therefore, for explaining what the first law of thermodynamics is, that's actually stated. The first law says that energy cannot be created, it can only be transferred amongst different forms of energy. So let's write this down. So energy can not be created. It can only be transferred amongst different forms of energy. So therefore, the first law is also often called the law of energy conservation. The law of energy conservation. Now actually, to explain what the first law of thermodynamics means, we have to ask ourselves the question, what actually is energy? So what is energy? And one definition is that it is a quantitative property that can be transferred to heat, work, or light. So it's a quantitative property. Transferred into heat, work, or light. And let's briefly describe what heat, work, and light are. And sorry, before I will do this, also here, let's underline this term here. It's a quantitative property, meaning that one can measure it, it can be quantified. So okay, continue with the original description of these three terms. So heat, so meaning this is, let's say, the energy transfer due to temperature difference. Energy transfer, or energy transferred due to temperature difference. So it has to do with the oscillation of the atoms in a solid. Basically that is some analogy to heat. And we said that since energy is a quantitative property that can be transferred into heat, work, or light, so there are different forms of energy, and they all can be transferred to heat, work, or light. And one example here is that for heat, let's say in the rice cooker, we transfer electrical energy, into heat. Then let's say work. So it's the energy transferred due to force imbalance. In this playlist there is also a video about the total or exact differential. There also a formula for work is given, namely work, it's the integral of a force vector times a differential distance. So this means that work is always a force a force times a distance, or in vector form a force vector times an infinitesimally small spatial vector. One thing would be you perform work if you lift up an object against a lift up an object up against the force of gravity, then you perform work on the object, let's say a tennis ball that you lift. And that will be one example for work, where in which, let's say, one uses chemical energy, let's say chemical energy in your muscles, and this chemical energy is transferred into work. And then the last thing is light. So light is generated when electrons in a solid, or when electrons change energy levels. So don't worry too much about this now. But one example would be in a light bulb. One also converts electrical energy into light. So good, now we have some, I think everybody knows somehow intuitively what heat, work and light are. So far we know there are different forms of energy. Let's say it could be chemical energy stored in chemical bonds. Let's say chemical energy is stored in fuel or somewhere in your muscles. And then there is also electrical energy. I think everybody has a feeling also what electrical energy is. And there are different forms of energy. This is not an exhaustive list of all forms of energy. It is just to illustrate what energy actually is, or how it is defined. And to further explain, after having addressed a bit the term energy, let's consider an isolated system. Let's say it's a cylinder, and in this cylinder there is a certain mass m, and the cylinder is completely isolated to its surrounding, meaning that no heat can be transferred, no mass can enter or leave, and then it also cannot be compressed. Then it's let's say an isolated system. And this isolated system has a certain energy, and this energy can be any energy, just as described before, but for this explanation example, let's say the total energy just consists of 3 forms of energy. But first let me finish this. So the total, or sometimes also called inner energy, of this isolated system just consists of chemical energy, work, and heat. And within this system, since it's isolated, the total energy of this system here, because it is isolated, cannot change, so it stays constant. But the only thing that can happen that within this isolated system, energy can be transferred from work to heat, from heat to chemical energy, or from chemical energy to work. I think now this pretty much explains the concept. And actually this is also sort of a statement of the first law of thermodynamics. And what I didn't say in the introduction so far is that the laws of thermodynamics, they are based on experience. So there are a lot of experimental observations or daily life experiences, and based on these many experiences, the laws of thermodynamics are stated. So it's based on experience and experiments, and after having had a lot of experience from experiments, the laws of thermodynamics were stated. However, mathematically, this first law of thermodynamics, meaning that the energy cannot be created, also can be expressed differently. It means, namely, that U, the inner energy, is most often denoted with capital U. That capital U, the inner energy, is a state function. So let's first write this down. So mathematically, the total energy is a state function. So what does this mean now? So let's underline this first, the state function. It means that energy change now for this description, let's drop that this system is isolated, so mass can enter, mass can leave, heat can enter, heat can leave, and so on. Meaning that this system here can exchange energy with its surrounding by, let's say, either work, heat, chemical energy, or some other forms of energy, and then its total energy changes. And the change in total energy simply depends on the difference between the two states. U1 would be the initial state after energy change, and U2 would state after energy change. So it does not mean. This means it does not depend. The change of inner energy does not depend on how you perform the change in inner energy. Say you could press the cylinder here and change its inner energy, and then if you press fast or slowly, it doesn't make any difference as long as the compression is in the end the same. But also in this playlist, such a property means that the differential change in U is a total differential. So du is a total or exact. So in English language, it's more often called exact differential. I think du is an exact differential. So this means that the integral du from state 1 to state 2 equals U2 minus U1. And also that, let's say, if we change the inner energy of the system, and finally we go back to its initial state, so just by looking at the system before and after the change, we do not observe any difference, then this means that, let's say, the integral, the ring integral, if you start, let's say, at state 1 and end also at state 1, again, generally this is denoted with such a symbol, integral sign with a ring here. The closed integral equals, let's say, U1 minus U1 equals 0. And this must be true. This also is also an expression of the first law of thermodynamics. Because energy cannot be created, it can be rather transferred. And because this is true, also this is true here. An example is let's say a battery. Say example is battery. So let me draw a battery here. Plus, minus pole, connections. And actually, let me write this down. But why this is a good example for the inner energy. So the charging state difference, or the charging state difference solely depends on difference in actual charging states, but not on how one charges, discharges in between. So it matches with our daily experience that if I empty the charge in a battery, so the charging difference only depends on initial reading and final reading, and not on which devices were attached to the battery, or even if you recharged in between. Doesn't matter. This is an example for the first law of thermodynamics, meaning the law of energy conservation. So let's go back now to this description here, or this finding here that if the first law of thermodynamics is true, then this also must be true that the total energy is an exact differential. And for exact differential, as one can also see or watch in this playlist in the videos about the total differential, it means that du can generally expressed as the sum, let's say it runs from I to n, and the partial derivatives of u with respect to x I times dxi. And this means that u, first of all, is a function of n variables, and then if the u is a function of n variables, it can be expressed as the sum of the partial derivatives and this differential changes in the variable. Generally, this is generally the case. We have not specified now on which variable u could depend, but let's say, because in our introduction we had good examples of namely heat and work are allowed, then one could say that x1 is T, the temperature, and x2 is V, the volume. So let's also say this would be the temperature, and this here is the volume. And this can be reasoned as follows. Let's say that heat was more or less defined as the energy transfer when there is a change in temperature, and if you just consider volume work, meaning that if you compress something or you expand something, then also the volume changes. Therefore, the change in volume work somehow is related to changes in the volume, or is related to changes in the volume. And let's say we now have only heat and work and volume work are allowed, then and then x1 would be T, x2 is V the volume, and there are no other variables, then the total differential reads as follows. So it is partial derivative of U with respect to the temperature times dt plus du times a partial derivative of U with respect to V times dV. And often in thermodynamics, or in thermodynamics and not often, one puts the partial derivative into brackets and as a subscript the constant variable is denoted, which would be V here. And if you had more terms than here and this subscript, there would be more variables. Or let's complete this. Here the variable T is kept constant. And according to our reasoning before, so we know this from the video about the total differential, that the total differential has a form like this. If T and V are the variables upon which U depends. But yeah, and according to our reasoning, this first term here would be differential change in heat, and this would be differential change in work. So small w, small q denotes differential, small q denotes heat, and small w denotes work. But notice here that I've drawn the differential changes with these curly Ds. This means that these two properties here are inexact differentials. And let's remember what this means. If differential change in heat and differential change in work are inexact differentials, it means that the ring integral of dq generally does not equal 0, and the ring integral of work also does not necessarily equal to be 0. That means that there is, let's say, no function v that w that depends on several variables, and which then allows to calculate the change in work. This simply doesn't exist. So things like delta w or delta q do not exist. So also again, for clarity, delta w equals w2 minus w1. So this doesn't exist. Okay. But to sum up now, after this reasoning, when only allowing forms of energy being heat and work, one can write changes in the total energy as delta U equals Q plus W. And Q equals integral of, let's say, from state 1 to state 2 dq, and W equals dW. If one evaluates these integrals, then heat and work, changes in heat and work, they have no delta because they are no state functions, because Q and dq and dW are not exact differentials, they are inexact differentials. And because they're inexact differentials, the D here is also a curly D and not a Latin D as here. Now one can also give a good example of why the inner energy is a state function and why heat and work are not. Let's say you want to climb a mountain. This would be a mountain. And you start here at height 1 and you end up at the top. So top would be at height 2. and you go up, and on top you cool down again, refresh, and then your body condition is essentially the same here and here. Let's assume this. And let's say there is one very easy path. That would be path 1. And one very difficult path. So the yellow path is path 2, the difficult one. So, according to the first law of thermodynamics, there should be a function for U that describes the change in inner energy. And by climbing the mountain, we have changed our potential energy, meaning that mass times gravitational constant of Earth times the height difference is the change in the potential energy. And this would be equal to U2 minus U1, and U generally would be mass times gravitational constant times actual height. Okay, we have changed our inner energy, and there's a function U that describes this change. But for the harder path, path 2, so let's say W2 is much higher than W1. Because we have performed work on our body, and per convention then the work is positive, but we had to invest much more during the harder path than during the more easy path. And what is also the case is that if you go uphill, then on path 2 you sweat much more, or your body temperature is maybe higher, and then maybe you have to walk longer. However, then you transfer a certain amount of heat from your body to the environment. And if, let's say in this example, your body is the system, and then your system loses heat, and if heat is lost, then heat is to be defined negative. And this means that Q2 must be much smaller than Q1. But this example actually illustrates that for the same change in the inner energy, work and exchange heat are different. As predicted, U, the inner energy, is a state function, and different du is an exact differential, but dw and dq are inexact differentials. Therefore, also the total work and the total heat are path dependent. And here, but again, let's finalize this. The delta U for path 1 equals the delta U for path 2. Actually, this is already the first part of the first law of thermodynamics. In the next video, the second part, I would like to give some examples by utilizing the concept of the ideal gas. So hopefully see you there.